environmental engineering. And we're very grateful that he's made actually a trip up to GISS to meet us all. So he's going to talk to us about subgrid heterogeneity. He's also done LES simulations and all sorts of things with machine learning too. So maybe you can pick his brain more at the discussion. That's going to be at 3 to 4 p.m. today too. So Nate, take it away.
Thank you. Hey everyone. I understand this is pretty informal, so please ask questions throughout. Like I am expecting that. So if you have a dying question, don't hesitate. And I'm going to do this seated if that's okay with everyone. Yeah. So I guess my full name is Nathaniel. I like to go by as Nate. And yeah, I'm going to talk about HydroBlocks. So the way I tend to give this talk is there's the talk that I give, the general talk. There's a talk that I give to model centers. So this is a little more on the, I want to say technical, but I'm speaking more in terms of the model language. And hopefully that's able to, we're able to connect along that. And yeah, as questions pop up, feel free to let me know. So just to make sure we're on the same page. So when I think about heterogeneity, in this talk, I'm not going to necessarily talking about continental scale heterogeneity. So I'm not thinking about Mountain West versus East Coast, right? Here I'm thinking more of landscape heterogeneity. I'm thinking, so this is how I think that you're flying on an airplane. What do you actually see as you fly out? So you might have in the Midwest, your pivot irrigation type of setups, different Bowen ratios, very drastic Bowen ratios you're going to get between those two different landscapes. Topography, so thinking about elevation gradients, ponds, small river networks, that type of heterogeneity is really what drives a lot of what I do. And in the context of what we do, so we can think about it in terms of multi-scale spatial heterogeneity. There's the continental scale heterogeneity, which all of our models already represent, right? It's more of a distributed sense. So if we have a 1 degree, whatever size of the pixel we have, the gradients along the continents, we're already almost quasi-explicitly representing that. The interesting part for me is thinking now about going into the subgrid question. So this is over the Southern Sierras in California. This is from a paper in 2018 where I kept developing this idea of HydroBlocks, which I'll talk about. And this is a classic representation of, we can think about this as a macro scale grid cell. This is 25 or 25 kilometers, so a quarter degree by quarter degree. And even in that size pixel, you've got a lot of heterogeneity happening. So in this case, you have your uplands versus lowlands. In this case, your uplands is getting more precipitation for more graphic effect. Temperature is very different. You have very different vegetation happening in those uplands versus lowlands. So that's more of a larger scale within that subgrid. But you also have other stuff happening. So up here, you have these different patches that are happening over here due to some hill slopes. You got some south versus north facing hill slopes right here. So you've got some differences that are popping up, just seeing from Landsat, from the vegetation. And then you have these river networks. So you have these river networks, which are effectively taking water from the mountains and redistributing it downstream. And it's effectively providing water for these riparian zones. So you have a lot of different processes that are happening in terms of along these riparian zones than close by in the areas that aren't getting as much water. And then you don't see it right here, but here you have a little bit of agriculture, etc. So there's a lot of this heterogeneity we think about. And we can think about Bowen ratios, we can think about runoff generation. All of these processes, prognostic variables, however you want to look at it, can be slightly different and many times drastically different, depending on the patches that we're considering. So this is connected a little bit more to a project that I've been working on for the past 4 or 5 years, which is thinking about, okay, so we have all of this what we call subgrid heterogeneity, which can lead to these very different Bowen ratios. This is a classic from Ronnie Avasar from 1989, showing the surface temperature of a homogeneous subbarren soil versus built up forest crops, which really set the stage where we think about these like tiles in our subgrid and our models, because these can have very, very different signals in terms of these Bowen ratios. And as a follow-up to that, I'm not gonna, I can talk about this at the end of the talk, but how we actually pass the subgrid information up to the atmosphere. All of our models currently, they effectively compute the subgrid spatial averages of all their fluxes per each time step and then pass it up, and the atmosphere effectively only still sees a spatial mean for the subgrid. In reality, if you do some large data simulations, this is from a 2016 paper, and my group, we've done some follow-up to this. But effectively, if you define the heterogeneity over the surface in terms of sensible heat flux, latent heat flux, and you prescribe the same atmosphere, organized heterogeneity, which is the top one of sensible heat flux, versus more disorganized, well, it can actually have a big impact in terms of atmospheric response. So top right one, you actually get deep convection, where the other one you get shallow convection. And the only difference is the organization that you have. The spatial mean and spatial standard deviation can be the same, but effectively the characteristic length scales can actually drive secondary circulations, which cause a difference. So in terms of what this heterogeneity does, it's not just a runoff generation question. It's not just a what is happening on the land itself, but it's also that interconnectivity between the land and atmosphere that we need to think about. Okay, so with that, introducing this idea of how we think about the subgrid problem. So how do we take that box, that pixel with all of the fine scale heterogeneities, and how do we actually represent that in macro scale models? I'm gonna say macro scale, anything above, I'm gonna say 10 kilometers, I'm gonna consider as macro scale. For the context of this discussion, we're gonna think primarily in the 1 degree realm. But a lot of the concepts are gonna apply to all of those. So numeric weather prediction, so medium term range prediction, so ECMWF, GFS, weather models, climate predictions, and also for continental global scale flood and drought monitoring, where we take satellite data and we prescribe it to a land model and want to make some effectively predictions or real-time monitoring of the hydrologic cycle. Okay, so what I want to talk about first is really talking about the methods that I started working on 10 years ago. I then implemented my postdoc at GFDL, and I've been working on contingency for the past 5 years at Duke. So how do we represent this effectively and efficiently, this subgrid problem? And then I really want to spend some time on the future of where I see the tiling schemes going. This is related to a workshop that Nancy and I were at a year ago, talking about where I think the subgrid problem goes and the concept of Earth system models. So the way I want to start with this is thinking about what is the dream approach. As a hydrologist, as a computational hydrologist, what is the dream approach? Well, the dream approach is going back to something we've been trying to do for many, many decades, was just fully distributed models, which is effectively model everything everywhere, which is a cute idea. And in theory, I mean, people have developed models that they are able to run over like the US at like kilometer spatial resolutions of entire 3D groundwater model with a land model coupled to it. The problem with that is that A, the computation becomes very high, and B, the uncertainty in the parameters is so enormous that it's not entirely clear what is the actual gain from it. And the concept of Earth system modeling, what we're coming from, we don't want land to take up 99% of our computation, right? We want land to be still pretty small. Yes?
Question, what do you mean by uncertainty in parameters?
So soil parameters. So let's say that we spend enormous amount of computation on the land to run a fully distributed 100-meter groundwater model over the entire US. It'll work, right? We'll actually have flow patterns, etc. But what is the actual gain of that when the uncertainty that you prescribe in terms of hydraulic conductivities into your model or porosities is so large that you are able to do those simulations, but a deterministic simulation isn't necessarily going to be everything that you wanted it to be, type of thing. So is it worth that computation with the uncertainty that is effectively in the process representation and also in the parameters in the model?
Is the uncertainty in the spatial distribution of the mix of different soil types or in the properties of a given soil type? I don't know how to put it because I'm not.
Both is the way I put it. So, I mean, it's not just also soil types, it's also like aquifer properties, right? So, so soil types themselves, there's going to be a large distribution of like the types of, you have like vertical properties of the like hydraulic conductivities. There's going to be a very large distribution to where you are in terms of properties, but in terms of mapping the soil types themselves, that's also a big problem. The main story here is that there's large amount of uncertainty in parameters and fully distributed mapping of parameters. We try to do this. My group tries to do this, and you can quantify uncertainties with it. But in the context of what we try to do here, which is we're trying to first use land model in a larger Earth system model and hope that the computation is small enough that we can run it pretty quickly. The applicability for our problems is not the greatest. We want something simpler. That doesn't mean there isn't a world for this, right? So in many ways, a lot of the parameterizations that we develop, we're going to use these types of setups as a way to do our solutions converge on that, right? So I still am going to use the same data that they're using, but that doesn't mean that's what I want to use this thing exactly in my Earth system model. Does that make sense? Any other questions about this? Okay. So these approaches generally are going to collapse, not necessarily collapse, maybe they're not appropriate for when you want to model these meter scale heterogeneities over continental to global extents in, for example, our system model. So more like they're not necessarily practical for our types of problems. So what is the alternative? And the alternative is this idea of we simplify the subgrid spatial heterogeneity. This is a chart or flowchart diagram that Eric Wood put together in 1992, the original version of it, and that Krista Peters-Larg updated in a paper 6 years ago. And it shows nicely this idea of one extreme of this is distributed models. This is the idea that every pixel in a, say, 10 meter, 30 meters, 100 meter distributed model has its own properties, and you solve effectively each pixel. And then the other extreme of it is the lumped. And the lumped is, in the context of our problem, would be to take my entire 1 degree grid cell and just assume homogeneous soils, homogeneous vegetation, homogeneous everything. So there's effectively two ways to view this. And what we are interested in is the sweet spot. So for those that know, I mean, think about the word tiles. Tiles is where I'm going with this. So you can think about the sweet spot as somewhere where you're not necessarily lumping everything together. You're not just homogenizing out all the heterogeneity in that subgrid, but you're also not going to go for this fully distributed model every 10 meter, 30 meters, 100 meter pixel type of question. Instead, you're going to look for how to effectively group things. And what I mean by group things, the way I like to think about this is grouping by similar environmental characteristics. So think about uplands versus lowlands. They're going to have similar properties, similar functioning. Riparian versus non-riparian, trees versus grasses, north versus south facing slopes, natural versus managed, steep versus flat.
Can I just ask a very stupid question?
Yeah, go ahead.
What does riparian mean?
Oh, so riparian, so effectively the idea is if you have like a stream and you effectively have the ecosystem along the stream, you effectively have more water there from effectively the stream bringing in water. It's not necessarily stream, it's effectively going to be the ecosystem around the stream, right? So you're gonna have all that land and it's interacting, and you just have more water availability. So you can have very different, like effectively biodiversity there versus like just 100 meters up the slope. That makes sense.
They tend to be wetlands, right?
Yeah, they can be wetlands, but I mean, you also get it in, I mean, in California, like you get this a lot, where you're gonna have up on the hill, so it'll be pretty dry grassland, but then down there, you're gonna actually have trees. So, but wetlands would be an example of this.
Does the semi-distributed approach necessarily keep the spatial structure?
That depends on the semi-distributed approach, yeah. So what I'll talk about is the hope that we develop a semi-distributed approach that gets this, right? That does something about getting that spatial structure, but there are semi-distributeds where it's all just completely spatially abstract, where there is no spatial structure, and there are the ones that are trying to get to actually including some spatial structure in there.
The HydroBlocks which you're going to be talking about
Yeah.
is a semi-distributed,
It's semi-distributed, trying to get the spatial structure in
and
there.
it tries to get the
Yeah.
spatial structure. Okay.
Yeah. Any other questions?
Question.
Yep.
So your environmental characteristics, I mean, some of them are clearly going to be correlated, like riparian is going to be with lowlands, right?
Yeah.
Not uplands
Yep.
generally. But do you have like a matrix of all
Yeah.
of these possible characteristics? And then,
Yeah, so
Yeah.
the perfect setup for the following steps. Yeah, so I mean, there's a lot of covariance happening between a lot of these properties, right? Like you have a lot of like things that are interacting. So in many ways, you can use one to represent the other type of question.
What is north versus south?
So if you see right here, you see these slopes. So this is south facing slope. This is north facing slopes. So you're actually going to have, because you just have effectively different surface energy balance from solar radiation, you actually can have warmer slopes than colder slopes, just north versus south.
Equator facing versus
Yeah.
equator not facing.
Yeah. There you go. Anything else? Okay. Okay. So what we want to do then is think about how to parameterize this subgrid spatial heterogeneity. So this is what I'm going to talk about here is this is nothing new. I mean, we do this in all of our land models. We have these different patches. How we construct different subgrid patches varies by models. So we have the classical tile approach, so split up into vegetated lakes, urban, glacier, crops. You can have some subdivisions within that. Other ideas are the lower right one, where you can split your grid into elevation bands. So think about orography. Just take an elevation data and just split them up into like uplands and lowlands. A very simple split. The other piece of work that's been going on a lot over the past 10 years is thinking about hill slope hydrology. So how do you think about hill slopes in the context of this subgrid problem? And there's the idea of a characteristic hill slope, which I'll discuss more a little bit further on. So the background from my perspective on this is, as we think about this subgrid problem, we also need to acknowledge, for the purpose of developing our system models, that we also have a lot of data of what the heterogeneity actually looks like. So over the globe, with varying degrees of accuracy, this is the parameter problem. But in terms of elevation data, I mean, we've got over the globe 30 meters, relatively good elevation data. Soil data, that's a little bit more uncertain, but we do have information that gives us a general idea of what the soil types are at like 100 at a 1 kilometer, 100-meter spatial resolution over the globe nowadays. Land cover maps, these are all Landsat, Sentinel-2 derived type of map products, but they do give us some sense of over the globe of what the land cover might look like. And then climate, that's more like, can you come up with like microclimates, more like a spatial interpolation, leveraging different data sets. But the main point of this is, how do we actually then take this data, which tells us something about that, where the riparian zones are, where the uplands and lowlands are, and how do we leverage this data to inform the subgrid problem within our land surface models? So the way that I think about this is more as a clustering problem. So this is more of a data-driven, trying to just take all this data and learn something about it in terms of what are the characteristic units of it. So how we think about the land model surface process representation, that's not necessarily going to a priori change, but how I define these patches is going to be a little bit more driven by what the data tells me instead of what I want to impose on the system. So what do I mean by that? So here's an example of that quarter-degree box over the Southern Sierras in California. So what I'm showing here are two different maps. Those are maps at a 30-meter pixel spatial resolution. So I think it's roughly 1 million pixels. And the porosity map comes from the Polaris data sets, and then the elevation data set comes from the National Elevation data set of the US, which is a combination of satellite remote sensing and on-the-ground surveys over the past decades. So what I'm showing here then on the bottom is I'm just taking each pixel and I'm comparing it to the corresponding value of porosity versus elevation, and I have a scatter plot. And I'm going to take a pretty naive clustering approach, which is k-means, and I'm just going to group those pixels or those points depending on their porosity and elevation similarities. So this is more like a Voronoi diagram. It's not really a clustering exercise. You're just effectively just partitioning your space, is a simple way to put it. So here I partitioned into 4 different units. And then what I can do actually is then figure out in space where those units actually are. This goes back to the idea of, is it abstract, right? So it's spatially distributed in the sense of the semi-distributed because I still know the location of where these pixels or where these clusters are. Right, so I've reduced my my complexity of my data down to 4 clusters, which I'll show have their own properties. But I still know in space where these clusters actually belong, depending on the data. Okay, so throughout the talk, the terminology is going to be a little bit, can be confusing. So in the concept of more data science type of question, this would be a clustering exercise. In land modeling world, we know this concept is like a tile. In hydrology, we can see this as what we call a hydraulic response unit. The terminology is going to change depending on the paper that came out, because either is for hydrologists, for land modelers, etc. But just let me get across that I'm trying to say the same thing, right? And I'll try to stick to the idea of a cluster because that's closer to how I'm thinking about this problem currently. So before I jump, yeah, go ahead.
I'm just wondering how well we know porosity. Is it satellite data?
No, so the porosity in this case, so this is Polaris, which is derived from Sergo. So this is all based on soil survey over the US over the past 100 years. Soil surveyors go out, they dig their shovel, they dig their pedons, they look at it, and they say, okay, this is an organic layer, and they effectively associate a soil type, and then they go back home and they draw a map.
So basically, globally, we don't have.
So we do. That's what soil grids is, right? So soil grids is what we would consider as the most contemporary global soil data set, and it's based effectively taking all these soil pedons over the globe that have been collected, and then using satellite remote sensing data as covariates, as predictors, to then develop some regression model between your in situ data and your covariates, and then produce a map. Over the US, over Europe, where we already have an enormous amount of in situ data, it does pretty well. Over other places where it's data sparse, it has its significant issues. But this is what soil grids currently is the most contemporary global wide data set that we have for soil information. So before I move into how this actually plays out in terms of land model, one thing I want to get across is that you can extend this problem to n-dimensional space. You don't need to stop with like porosity and elevation. You can throw at it whatever information you think matters in terms of what is playing a role in the heterogeneity of the system, and you can cluster that data. Now, going back to the covariance problem, if you know that a lot of these are related to each other, aren't you just wasting your time? Because you had a lot of repetitive information. So I'm not going to talk about a lot here. So we've done some PCA on this data to try to reduce dimensionality to see if that brings out what matters the most. We've played with like weights and those types of things to figure out what is the optimal representation. And that stuff does matter and it does play a role, but we've learned that it doesn't change things a ton. Most of the time, as long as you are careful about how you choose your covariates, it'll be okay. That's our general experience. But so here is using more covariates, and there is tiles, which are usually clusters that would tend like. So there you're not just getting an uplands versus lowlands. Here you're getting north versus south facing slopes, uplands versus lowlands. You're getting a little more information in there with simply 10 clusters.
Is that a standard number then that you're suggesting?
10? No. So I'll talk about it. Very much depends on where you do this. So if you do this over the Midwest, where it's crops almost an entire grid cell and it's pretty flat land, you can get by with like 2 or 3. But in like the Mountain West, you might need like 300 of these before you're actually converging on there being enough heterogeneity in the system. What we've seen is that on average over the globe, if we were going to average out how many clusters you would need, you're looking at something of like 20 to 30. Is that number
per grid cell?
Yeah.
That's a 100-kilometer grid cell. Or,
Yeah.
Or 5 kilometers.
100 kilometers.
So if everything is split into 100 kilometers grid cell, 1 degree, then
Each of those would have to have around 30-ish tiles on average.
And if you reduce the resolution to say 50 kilometers, would that reduce the amount of tiles by substantial amount?
Yeah, it will slightly reduce it, but not as much as you might think, because there's other heterogeneities playing out there that are gonna matter. So you might go down to like 15, or like that's just like a made up number right now, but you still need to represent, you can't just have it, is the point. Or even a quarter of it.
And that stays stable even when you have like normal weather stuff, like you have big rain event, so you're more wetlandy and you don't have rain this season, so it's like,
Yeah, so this is like dynamic clustering. So this is now going to the question of like, okay, so I'm in a very dry part of the year. Why am I actually like modeling all this stuff independently? So you could actually like join things at the part of the year and then split them when things get more interesting throughout the year. Currently we don't do that, but you could do it.
I mean,
Definitely could.
this would have to be kind of dynamic, right? I mean, looking at temperature, precipitation, land cover, those are all things that change seasonally.
Yeah.
And or
Right.
from one year to the next, right?
So the one thing that I'll say is, so this implementation of it is more like your offline model where I'm running it for like short-term prediction. For the perspective of like an Earth system model, climate model, so the implementation of this at GFDL, I don't cluster on land cover. I don't cluster on. I'll cluster on precipitation temperature because it's like microclimate driven by elevation. But really, all that's being using it's clustered is going to be like topographic driven information and soil property information, right? So I'm assuming something static about my system. I'm assuming that topography in that case is going to be static enough that I'm assuming that there's not going to be some massive earthquake or landslide that's going to destroy a mountain.
Sure, but you said you also cluster on like temperature and precipitation, right?
but
So how does
In the
The number is
concept
set in
of
the beginning, right?
microclimate, right? So it's more along the lines of like,
No, but if you're looking at like projections, right?
yes, yeah.
Like, I mean, you know, particularly in topographically complex
Yep.
areas,
Yep.
right? We expect that these kind of
Are going to change.
temperature things are changing.
No, that's a good point. That's a good point. Yeah, so I mean, you could think about as things move forward, you can dynamically cluster it to change that orographic distribution. I mean, but what I would say is that I'm using it primarily as a way to create these like elevation bands. So is the orographic effect itself going to change in terms of like the wind patterns? So if the wind patterns are changing, then yes, then that precipitation from the orography is probably going to change. But if the general wind patterns are the same, what you might be getting is your snow levels might be different, right? But where is the maximum precipitation? It'll still be happening in the uplands versus lowlands, right? Type of question.
No, I mean, fair. I mean, I guess my question is, what is the, like, if you do want to have a kind of dynamic
Yeah.
tiling, like, what's the kind of computational burden that would add? Would that be pretty substantial, do you think?
I think what you would do is every year you would, so the process, so there's a pre-processing and then actually running the model. The pre-processing of this is a pretty small fraction. So what you'd have to do is every year at the end of the year, you map out your cluster information, all your prognostic variables, you map them out, and then you come up with effectively a new like microclimate maps, and then you just do a regrouping. It's possible.
so it's like
Certainly
when you do land ice model, and you do some sort of asynchronous thing, like every longer time scale to
Yeah, you could do that.
refigure.
Yeah, I mean, the only issue you'd have is like, you gotta be careful about like how you're gonna group together different like the carbon budgets. I mean, you have to be careful about it as well.
I mean, so have you done this kind of sensitivity tests where like, you know, here you have, you know, what are like 8 or 10 fields, right?
Mhm.
Like, and you get a certain clustering, like,
Yep.
like how different would be the results if you eliminated like the dynamic ones, like temperature, land cover, precipitation?
So generally, the temperature and precipitation are very useful because elevation tells you a lot, but elevation does not tell you that more rain is going to happen on the west side versus the east side of the mountains. Right? You need something to tell you that. Yeah.
Yeah, but you can't get that from a prediction, right? How do you know where if you're computing the precipitation on the fly, you don't have any observations of that precipitation landing on one side of the mountain or another side of it, right? So you can't.
You would have to do some level of like quote unquote downscaling of your projection for that next year onto the higher resolution map to then give you a updated version of what the microclimate would look like.
But within a GCM, that's not ever how you're going to do it, right? Now you could do downscaling, like on the fly downscaling, right? So we kind of do that a little bit for the land ice component, where we've got a very high resolution land ice component. But dealing with the precipitation in an on the fly downscaling way is like as far as I am aware, a totally unsolved problem.
Yeah.
Right, but the notion that you would redo this clustering as part of like an ongoing, I think that is.
I mean, the one thing that I will say is that, and I'll talk about this, so when you have all these clusters within the subgrid, what you also want is some way to, on the fly, downscale to the tiles themselves, right? So if you have all this complexity, right, the uplands versus lowlands, but that upland versus lowland is still seeing the same precipitation in the subgrid, right? Then in terms of vegetation is going to respond the same in the uplands versus the lowlands. It's also seeing the same temperature, same precipitation.
Okay, but we already have elevation costs.
Yeah.
Right. So part of the like the temperature gradient and the the surface flux gradients. I think we can capture already, right? But the precipitation thing, like just like going from the like a global a grid cell mean precipitation amount and distributing it over the elevation classes, right? We don't do that, and that's really, really hard just in and of itself. Right now, I mean, maybe you have an idea about how to do that.
I mean, there are approaches. I mean, like, over DOE, they did some stuff like 20 years ago, and like they implemented stuff that you have like orographic effect precipitation. There are some ways to do. The bigger problem actually is not for me orographic effect. The bigger problem is like convective thunderstorm, like thunderstorms. Like, how do you actually do like scattered thunderstorms in a sense that's actually not just completely random? That stuff is difficult. Yeah.
So we actually do have convective versus stratiform precip set up in the DCM. And Greg Elsasser has done a bit of this. So it's cryptic to me, but I mean, it'll have a portion of the convective precip a bit more of a part of the grid cell, for example.
Yeah, but I mean, the current way that we all do it, that this is done, is like, it's not necessarily informed by the subgrid heterogeneity. So like the land is not giving preference of where that thunderstorm is going to happen.
Yeah.
So like, in theory, you would want that downscaling to actually be informed by the land itself. So that doesn't happen in every models. And that's what I was trying to get at. Yeah.
Is there like a horizontal resolution where this starts to become flexible and tractable? Like, is that scale 1 degree or
What becomes more defensible?
all of these things you're proposing and
Well, I mean, from my perspective, all this stuff, you can go down to the very finest scales. I mean, like, you can apply this stuff to a 1 kilometer spatial resolution. At the end of the day, it's just a way to take like field scale heterogeneity. So think about like 30 meter, 100 meters, and how do you summarize it in a way that represents what matters to the system. So you can run your model at a kilometer, or 100 meter, or 10 kilometers, 100 kilometers. And it also depends on the question, right? So if my question is flood forecasting, I need to be representing the heterogeneity next to my rivers really well, right? To get the inundation. If all that I care about is like climate means or seasonality, I mean, that's a different question. And so for our purposes, this is why I say 20, 30 tiles, because there's a lot of that fine scale heterogeneity is not going to play a huge role in our problems. But if I do this for, again, flood forecasting, in that case, I might need like 2,000 tiles. Right, I need way more heterogeneity if I want to actually represent a flood that's moving its way through those problems.
If you're going to use 2,000 tiles, why not just have much higher resolution?
Because the full resolution there would be 1,000,000 pixels. So if I did it 30 meters, there'd be 1,000,000 pixels. So even if I'm writing 2,000, that is still a significant amount of reduction that you're getting. Let me move ahead. So one thing I want to bring is simply just doing naive clustering is actually not ideal. Because you start thinking about the hydrology, just simply doing clustering is breaking up hill slopes. It's not necessarily the runoff generation can be a little bit wrong, to put it in the least. And this is the original paper I did of HydroBlocks in 2016. We showed this about this simple clustering is not enough to get the hydrology, the redistribution of the hydrology in the subsurface. So in 2018, the follow-up to this, and this is the work at GFTL, which was effectively taking within the subgrid, take the elevation maps, the high resolution elevation maps, delineate watersheds, or even go further and delineate hill slopes, And then do come into a similar idea. So take the hill slopes and take properties that we can think about are characteristic about the hill slopes. In this case, you might have like 4,000, 5,000 hill slopes, or 2,000 watersheds. Compute some average properties for each of those hill slopes or watersheds, and then apply some clustering to that. And then what you get is something like this. So this is now dividing all of your hill slopes in your domain, in your subdomain, into hill slopes that are north facing, some that are south facing, some hill slopes are high up on the uplands, some hill slopes are down in the lowlands. The exact same idea what I just talked about, except we're actually grouping the entire geomorphological unit instead of just clustering random pixels. So without going into too much more detail about this, I want to actually get into how this actually works out. What the most current iteration of this, and this is a paper that came out 2 years ago, is instead of thinking about grid cells, I like to use the term macroscale polygon. A regular grid can be macroscale polygons, but this idea can also be used in watershed space. This is as hydrologists, we like to create models that instead of regular grids, they're just like watersheds. This is like slight change on a regular grid, just so that I'm not breaking off hill slopes between grid cells, but you can still use a regular grid. Within each of those macroscale polygons, I then apply this idea of clustering watersheds. And the other one was hill slopes. This is watersheds. So I'm grouping watersheds by similar characteristics. Then I'm actually taking each of those hill slopes and watersheds and those characteristic clusters, and I'm discretizing them. So I'm effectively allowing for this riparian, non-riparian zones to be represented within my characteristic watersheds or hill slopes. And then with each of those height bands, then I actually then cluster on soil and other information to allow for what we call sub-height band clustering. And then what you end up with something like this. So this is now your map of tiles within this grid cell. So you have a lot of information happening along these along the rivers. Those are separated from the hill slope, from the uplands up here. And it's now a little bit more consistent with the geomorphology that you would expect. It's going to play a large role in your hydrology. So it's like a hierarchy. The hierarchy is watersheds. Those watersheds now are split up and discretizing the height bands, and those height bands have sub heterogeneity within them, which is then these like clusters that are effectively different soil types. So, any questions about that before I move along? Yep.
I have a question.
Yep.
So, for different subcomponents, you have different clusters. So, say
Well, when you say different what do you mean by subcomponents?
say for water cycle, for the water flow, so
Yes.
you can separate them into different catchments. But for vegetation, you need to cluster them according to the vegetation types, right? So when you do the interactions between those subcomponents, how do you do that?
When you see the interaction between the tiles,
Interaction between these components. See, the water flow, the water condition for vegetation, because you cluster the
right. So the way that I would say is, so each tile, right?
Mhm.
So go down this hierarchy, right? At the end of it, what you end up with is a series of tiles,
yes.
right? So what you end up with is a fancy way of coming up with like 10, 20, 30 tiles. Okay. Each
This tiles. This tiles.
Yes.
This tiles include each of them. All
Yes.
all the components.
Yeah, so each tile has all the components. It has the vegetation, it has the soil, it has its own soil model, soil properties, etc.
Okay.
And it
So-
solves water, energy, carbon, like within that column.
Okay. So you mean you don't have to you don't cluster them and then do factorization. You do that before. I mean, you do the computing before clustering.
So I do the clustering to arrive at what are my characteristic tiles that are then going to drive differences in the carbon, energy, water cycles. But then the actual solving of the carbon cycle, water energy cycles happen within the tiles themselves that I've built from clustering.
For each tile, it does it then column.
Uh-huh.
So what about the subsurface then?
So, yeah, so there is interaction. So I don't know if I have a lot of it here. Part of this thing right here, this characteristic hill slope, one thing that we've added is along in a watershed, so in a characteristic watershed, as we discretize along these height bands are allowed to flow into each other, right? So you can have water flowing from the upland height band to the lowland height band within that watershed. So what you'll get is effectively convergence of more moisture into the riparian zones down here. So effectively the uplands are supplying more information or more moisture into next to the streams. And then one thing you also think about is like you can actually have groundwater happening between watersheds. So you could actually have this cluster of watersheds interacting with this cluster of watersheds, effectively exchanging subsurface information. And that's something also we're currently exploring. But that's in development. The hill slope groundwater, the hill slope subsurface interactions, that currently exists. But the interaction between clusters of watersheds does not exist yet. So main story of all this is there's a way to create via clustering these tiles to leverage all this data. And then this information is then used as your tiles within the models themselves. So reiterate, the model is not actually seeing a map of tiles. The model is seeing a statistical distribution of the tiles or HRUs or clusters with associated properties, meteorology, and interconnections. Interconnections is like effectively how the subsurface talks to each other. The model this was developed when I did this originally. This is called HydroBlocks. This was then merged and take a lot of these ideas and implemented at GFDL. Martin Clark, when he was out at NCAR, did this with SUMA and CTSM at the one have a CSM. They have similar ideas they're putting in there as well. So how we think about the subgrid heterogeneity, there are a lot of growing similarities in terms of leveraging data and constructing these hill slopes around them. Okay, so I'm going to walk you through briefly how this actually plays out in practice. So think about it first we create these clusters, and now how do I actually construct the information for each of these tiles? Well, I have this map of porosity, I have this map of clusters. I effectively then compute the average porosity for each of those clusters. And so I end up with cluster 1 at layer 0 to 5 centimeters, has a porosity of 0.43. Cluster 2 has 0.44, et cetera. So I effectively come up with these characteristic properties for each of the clusters or tiles. And so you might have clustered on porosity and elevation, but then you can also carry along the rest of the properties with you. So I've clustered on this, but then because there's a strong relationship with other soil properties, it also brings a lot of that variability with it along as well. The other one is, this is more of an offline application of this. So if you have a way to downscale it within a subgrid downscaling, this would also be applicable. But effectively, if you have some high resolution distributed meteorology that's higher than the grid that you're running at, you can actually compute which are based on the cluster map, you can figure out which of the meteorological grid cells correspond to your tile, and you can actually arrive at a characteristic, effectively, time series for that cluster of the meteorology. Basically, in the uplands, you're going to have lower temperatures, and in the lowlands, you're going to have higher temperatures. And similar idea for precipitation. The point is that you don't have to use a uniform grid cell meteorology as prescribed to the tiles. So if you have information that you can use for that, you can use it. Or if you have a way to downscale, you can use that as well. And so put those two together. So you effectively have a way to construct model parameters. You have some way of hopefully downscaling meteorology, or if not, you're just using the grid cell mean. You put that in, and then you effectively solve at each of those tiles. And it all comes up with its, effectively, in this case, land surface temperature. Think about water, energy, and carbon. And then one thing I want to point out is because you're saving these clusters, these maps of clusters, this actually provides a way to give you a sense of what a fully distributed simulation looks like. So here, what I'm showing here is you take these this one time step, you have 4 different values of land surface temperature. You have this map of clusters. Well, you can immediately just map it in space. So it enables you a field scale estimates of what the subgrid model output might be. Okay, so I got 14 minutes left, so I'll try to make it through quickly. Another way of seeing this, so this is, here's your map of tiles, here's your meteorology, do all of that stuff under the hood. What comes out on the right there is these different time series of evapotranspiration. The ones on the top, the red and the pink one, those are actually 2 different, so they're 2 different hill slopes within this grid, right? So there's one characteristic hill slope that's up on the uplands and one that's down in lowlands. And what you end up getting is the height bands within those that are closest to the stream. Those are higher ET because you effectively have convergence happening. So you have an accumulation of moisture, and then you have a lower ET signal happening in the uplands of those hill slopes. And then one thing that I want to get across, and I can talk about this later in the discussion, but again, we do all this fancy stuff with our models, and you don't need to, we can use data, we can all these patches, but at the end of the day, what the atmosphere still sees is only this black line. The atmosphere itself has no idea what's happening here. This is just simply for us to solve, but there's a problem because we're not actually passing this information up. So even though this can play a role in the atmospheric response, it does not, that coupling does not exist. Let me skip over this, make sure we have enough time.
And how would that black line compare to if you didn't do all of this subgrid heterogeneity?
Yeah, so let me show you where I got it right here. Okay. So this is not the exact answer to that question, but it's kind of getting that. So the way I interpret what you're asking is how does that black line change as you increase the number of clusters, right? So I see this as like a convergence question. So how many clusters do I need before it stops changing? Type of idea. So here what we do, and this is a 2018 paper. So this is over that site in the Southern Sierras. So what we do is we start increasing the amount of heterogeneity. The first case up here is going to be completely lumped model homogeneous. There is no heterogeneity in the system, right? So that's one tile. Next, we increase the number of characteristic hill slopes. So there we have an upland versus a lowland, but there is no discretized height bands. There is no intra-band clustering. And here we increase the number of hill slopes a little bit more. Then we start playing around with discretization of those hill slopes. So there you're starting to get your riparian versus non-riparian areas. And last, although you can't see it because a lot of it's quasi-spatial noise, when you start playing around with sub-height band soil information, then you add a little bit more heterogeneity. So here you're just playing around with those different parameters that are controlling the heterogeneity of your system, and then running your model and seeing how, in this case, the mapped out transpiration of the annual mean actually changes. And to get to your question, although I'm not necessarily showing you the time series, but I'm showing some summary statistics. So each of these dots is going to be a given water year. So I think I'll show it over here. Yeah, so this is like 2003 to 2014. So what this is showing is the spatial mean, so the average of all of these points. And then I'm showing how it changes as I increase the heterogeneity of the system, as I increase the number of clusters. And so what you see with the homogeneous one is the mean is higher, right? Now, this, depending on your setup, it can be the flip. Like you can have that the mean is lower. There is no reason why this is always going to be the case just like this. But you do have this convergence properties where you start, it changes quickly, and then it stops changing. You look at the spatial standard deviation, which is a metric of the heterogeneity more than just simply the mean. And again, it changes a lot, and then it starts to stop change. If you look at actually the summary of this, of where things actually start to calm down, there you get into like the 300 tile world. And the exciting thing is if you do this for a lot of different variables, so we do runoff, we do transpiration, net primary productivity, leaf area index, and this is with the GFDL land model. Base flow storage change, sensible heat flux, root zone soil moisture. A similar story pops out, which is all of this is effectively converging. And it's converging at this 300 tile level, and again, I'll go back to the point of how many tiles do I need. This is a very highly heterogeneous domain, right? I could show you other places where it'll converge after like 3 or 4, right? But on average, what we see, it's around 30 or 40. But the main story that I would try to get across here is that going back to the fully distributed models of modeling everything everywhere at 100 meters, you don't need to. And it's not just you don't need to because it's too much computation. You don't need to because for the purposes of what we're doing, you converge on that solution with a very small fraction of the computation by doing this clustering. And so in this case, you converge in 1/1000th, 1/10,000th of the computation on pretty much the exact same macro scale response. So for the purposes of what we're interested in Earth system modeling, we're already getting what we need with a very small fraction of clusters compared to the number of pixels of the entire 30-meter resolution. Okay, let me jump to the last part to make sure we cover that. I wanted to go over the highlights of where I see tiling going, and I recast it in the concept of this clustering because it gives us a lot of flexibility of what we can do. So my first point is tiling exercises, when possible, should be recast as a clustering exercise. That's really what we've been doing, especially when we do this on data. So like land cover tiles, we're really just clustering. We've just never put it in that framework. The second one is if you actually save these tiles and have this information, it actually allows you a way to map your tiles for applications evaluation. So when the in situ soil moisture probe comes along and we have no way to actually validate our offline model, our argument tends to be, well, scales are different, therefore we can't compare them. But what this allows us to do actually is to break that dynamic, and actually, if you have the right number of tiles, you can actually quote unquote downscale, but you're not really downscaling, you're just mapping out the tile information to its corresponding cluster, and you can actually figure out what that simulation is at that given in situ probe for like 100-meter pixel. And generally the result is depressing in the sense that we realize in reality the properties in our models and the process representation are not great. But it allows us, it doesn't allow, it forces us to actually be a little more critical of our models instead of saying scales don't match, therefore I can't compare. Third one is optimal tile configurations. So instead of just saying, should I do 10? Should I do 20? Should I do 5? Like, what should my tile distribution look like? This idea of convergence allows us to develop algorithms to optimize for a given problem. Am I doing flash flooding? Am I doing annual means? How many tiles I actually need to actually converge? The fourth one is this idea of evaluating simulated subgrid heterogeneity. So we develop all of these subgrid parameterizations. All different centers have these different parameterizations in place. But do we actually ask the question of, are they actually, the simulated subgrid heterogeneity, is it actually realistic? Is it actually adding realism to our system? Or is it just something we put in there because we think that it should play out? And the nice thing about this mapping out concept is that it allows us to also compare to remote sensing of LST, remote sensing of leaf area index, you name it. It allows us to put it in the same world and not just have to compare spatial means at a 1 degree. It allows us to compare it 2 kilometers of what's actually happening as satellite remote sensing might see it. This is a follow into that. So this is what we did with the GFDL model. So we compared Copernicus LST, which is a global 5-kilometer LST product, and to figure out how like the subgrid spatial variance of LST was doing. And this is very preliminary, but in general, it just highlights where this subgrid heterogeneity is actually doing what we thought it was, and where it needs some work. And generally, most places it needs some work. So the one I wanted to point out, and this kind of goes to larger data simulation stuff, this class project that I've been leading for the past 5 years, it's trying to develop parameterizations to actually take all this subgrid tile information, not just passive spatial means, but actually pass up the heterogeneity information into the atmosphere. So you can actually see the response. This is some large data simulations where we did with different surfaces. So this is a completely homogeneous surface. And here we add river heterogeneity, soil heterogeneity, land cover heterogeneity, only meteorological heterogeneity from effectively a scattered thunderstorm from the previous day. and then fully heterogeneous. And this is actually the sensible heat flux spatial patterns in this 100-kilometer box around the Southern Great Plains site in Oklahoma. And what you actually see is, here's the response in liquid water paths, so effectively clouds. So these situations right here, when you force the atmosphere with it in a large data simulation, get you this response in terms of cloud development, where you have some peak in the afternoon and it falls off. This structure right here that's imposed by a scattered thunderstorm the previous day leads to secondary circulations by these large patches that actually then leads to an enhanced cloud development. So everything else being the same, simply the structure of the heterogeneity actually can have a big role in the cloud distribution. The other one is intertwining routing and tiling schemes. So one thing that we've been doing a lot is rethinking routing and how do you actually bring in these watersheds and all of this heterogeneity we've been thinking about and actually use subgrid routing schemes that are actually not just grid box to grid box, but actually have the tiles talk to these fine scale river networks within a grid cell. And then allows to intertwine the two and you have to be able to inundation in that context as well. I'm going to run through the last one because I know there's like 3 minutes left and then we can stop for more questions. The last one is thinking about connections between these different tiles. So we've done this in the context of water in terms of subsurface water. How that plays out is something like this. So this is down here, these tiles are next to the river, and HRU1, this is going to be up in the uplands. And this plays out in terms of late heat flux is higher next to the stream and lower in the uplands. So pretty much exactly what I showed for the previous example. But my argument actually is that this idea of connectivity between tiles can be used for a lot of other stuff. Why do you have to stop at subsurface to surface flows? Why can't you think about fires? So effectively, if you know the connectivity between tiles in your subgrid, if you know your wind direction, you know the wind's going to flow from tile 1 to tile 3, you can think about the fires being pushed from this tile to the other tile. And that can change depending on your wind direction. Seed propagation. If you know the wind direction within your tiles, you can say that seeds from tile 5 are going to go into tile 6, right? So you can actually have a more spatially informed tile structure that allows you to spread information between them. Yes.
I guess we were starting out with having just a statistical representation of the heterogeneity, but here that's going to be spatially explicit if you know direction.
So what's going to be spatially explicit is you've done this the map of clusters, right? Within that map of clusters, I can tell you that pixels of cluster 1 are next to pixels of cluster 2. And I can tell you that 50% of pixels of 1 are connected to pixels 2. So I can effectively create a matrix of effectively connectivity between the different clusters. So that connectivity matrix, as you know, wind direction, you can actually figure out what, like, with the seed propagation, 20% of it will go into tile 2, 20% of it will 30% will go into tile 3, going from tile 1. We can talk about it more, but
okay, cool.
The idea of this would be like for fires. So if you know this is your connectivity happening between them, you could effectively propagate fires between the tiles. And this applies fire, blowing snow, dust emission deposition, nutrient transport, advection of heat and moisture, etc. So that's where I'm currently going with this. I'm very excited about this direction because I think there's a lot of potential, but there's also a big headache in trying to answer these questions of wind and how to downscale wind. And the last one, intercell subgrid tile connections. So in the 1 degree realm, this doesn't really matter that much because you can effectively assume that your 1 degree grid cells are effectively independent from each other. But the moment you go into like a weather prediction 10-kilometer grid situation or 5 kilometers, you need to think about how the grid cells themselves talk to each other. And not just simply the macro scale grid cells, how the actual tiles in this grid cell talk to the tiles on the edge in this grid cell. And so there's a connectivity matrix happening between tiles of grid cell 1 and tiles of grid cell 2 question. And that's a whole nother fun question I have a student currently working on. So fun problems. So with that, I can go over more details of other things, but I wanted to wrap it up here. I think we're out of time. So thank you so much.
take any more questions?
Yeah.
Please.
Let's go here.
Very interesting. I'm wondering when you're showing those, or when you were saying that there's convergence between like order 300 tiles and full resolution, are you also changing the atmospheric resolution?
No. So in that case, all that I'm doing is so that's an offline simulation, right? That was an offline simulation, and I have a meteorological data set that's over the US, like a 4 kilometer spatial resolution. So I have temperature at 4 kilometers, I have precipitation at 4 kilometers. So that is constant. So I'm using the same data set for all those simulations. Only thing that's different is that each of those tiles is going to see a different meteorology. But the average of all those tiles is always going to have the same meteorology across the different experiments. That makes any sense.
Yeah, I guess I'm just wondering if you start also changing atmospheric resolution, how
Yeah.
much it's gonna change, like precipitation.
It will. It'll definitely change.
And if that's gonna dwarf the effect that's captured by the tile.
I mean, generally what I would say is I would not recommend, like, the land in this case should be run at no coarser than the atmosphere, right? So if your atmosphere is doing 5 kilometer, then run your land at 5 kilometer, right? So in that case, like, yes, it'll change it, but then the question becomes a different one. If that makes any sense. But yes, running an online coupled model with different atmospheres will change it, for sure. Another question back there? Yeah.
So going back to your 278 tile example.
With the magical number.
Which you said is not representative globally, but
Yeah.
like, what if you pick your tiles not in terms of these other criteria, but rather to pick them for the fastest convergence?
Yeah.
Like calcium quadrature, you pick your duration.
So we just published a paper that came out December of last year. We do exactly that, right? So effectively we do like a search, like an exhaustive search of what is the optimal, like, number of hill slopes, optimal number of height bands, optimal number of interband tiles to minimize the number of total tiles and to get some objective. And you can get a wide spread. So you can probably get that 278. I don't know the example from this, but you could probably get that 270 down to like 60 or 70 if you're like careful in terms of how you do your search. There's a lot of like variability in terms of like what is the optimal number of tiles. But going back to one of the points that I made in this at the end is like, that is exactly a question that we need to be able to solve. Like, we need to know how to come up with optimal configurations of these tiles. So we get as much information as we want to, but we're also minimizing the overuse of tiles. Yeah.
Have you generated a map like for the continental US maybe to like number of tiles per grid cell at different grid cell sizes?
So I have it here. Oh, here, there it is.
Okay.
I'm not showing actually. This is actually the global one. So this is the one that we did at GFDL.
Okay.
So this is like, clearly there's no color bar, so you have no idea what you're looking at. Blue is like 1, so Antarctica is 1 for like pixels, and then this is, I think this was like 40 or 50 or 60 is what you're getting along there.
Okay.
So as you'd expect with the mountainous regions is where you need to throw it most. I mean, this becomes from a computing perspective, it becomes a load balancing nightmare. So unless you're willing to like split tiles across different cores, you need effectively to have one core has like 10 different grid cells that all have like 3 tiles, and then another core has a single grid cell with 200 tiles. If you don't do that, then it's really hard to make this happen.
Thanks. One more question. So have you gotten to the point yet where you've run a simulation with the GFDL atmosphere and seen any improvements in some climate biases?
Yeah, no. So we've done this. The short answer is not much.
Oh.
And the reason is because of the spatial mean problem.
Okay.
We're effectively, yeah, you do see some changes, but because you're still just feeding the spatial mean, I mean, it's going back to this question, right? It's going back to this question of like, at a certain point, things aren't changing that much. So what we develop here is a more rigorous way to actually define these tiles. But in general, if you have 10, 20 tiles in your model, you're already quasi getting into this realm, just from an indirect way. And what we see is that by just averaging everything up and passing the mean to the atmosphere, this is where things are gonna change when you go from 1 tile to like 5 tiles. After that, things aren't gonna change dramatically for the types of questions that we care about in terms of like an annual mean. For a flash flood forecasting thing, then yes, we've seen dramatic changes, but not for the concept of this. Yeah,
So given that this is, most of the stuff is gonna happen in the mountainous areas, and, you're gonna reach elevations where you're seeing glaciers and mountain glaciers,
Yeah.
presumably this just kind of smoothly fits into all of that, right? Not to be anything special
for glaciers, for what?
glaciated areas.
No, I mean, we've been talking about, I mean, currently, as this was implemented at GFDL, we have and land fraction, I mean, we have soil fraction, we have lake fraction, and then we have glacier fraction. We've only worked in the realm of soil fraction, right? Effectively vegetation and bare soil. That's where we've played around with this. We haven't yet touched lake fraction and glacier fraction. Those have still been separated. But this idea can hold for as well. I mean, you can cluster, we talked about this morning, you can cluster lakes. You could actually come up with like different lakes that exist just by taking your lake data set, clustering data set. You can actually have the glaciers, like in theory, you could have the lake glaciers quote unquote emerge, right? So you could actually have the glaciers be more connected with the actual topographic subgrid information itself. And that's where I would want to go with this, to not have this separation that exists between these fractions. This kind of goes back to the question, Nancy, of how, like the idea of like how you deal with wetlands. For me, the ideal world is there is no lake fraction, there is no soil fraction, there is no glacier fraction. For me, it's all the same world. One is ponded with water and it acts like a lake, and the other one is not. But the separation itself is always going to be a problem. We do it because it makes things simple, but that doesn't mean that's like how the actual. We need to think about it as like a continuous system.
Okay, so to follow on.
Yeah.
Part of the problem we're dealing with the very high elevation glacier areas is that they often see totally different weather, and they're often above the boundary, right? So anything that the mean atmospheric column is doing, it may just like it's irrelevant to what's happening at the highest peak, right? But it's there above the weather. Right?
Yeah.
The out deck is in the valley. So when you start to have very large gradients in elevation, then you can't be assuming that the atmosphere is homogeneous, right? Over these things, like even if you took into account the lateral.
Yeah, I agree. I completely agree with you. I think that we can create these tiles, and it can be very fancy, but if the downscaling of meteorology does not account for what you need, it's not gonna suffice for that type of problem. So yeah, we're definitely in agreement there.
So when you said you can make measurements because now there's no problem with scaling things up, right?
Well, there's no problem, and it's more like I'm
So-
able to connect it down. Yes.
So you have predicted like this very heterogeneous like cluster map. So if you sample intentionally from the same clusters, are you equally bad in all the clusters? Like how good is your clustering?
I don't know yet. Like honestly, in terms of like
Because
observations,
otherwise it's just like, oh, it doesn't match this cluster either. But the real, like to know if your clusters like have meaning, don't you need to first
the
say,
variance within the cluster itself.
don't you need to say like the clusters, like your on the ground measurements, not something that you've trained it for? Those things themselves like are coherent?
Well, so the question number one is the data, so in theory, if the data that I'm using to describe the clusters is good, right? If the soil properties that I'm using to create the clusters is accurate, and everything else is accurate, and we know that soil properties, land cover properties, topography are what's driving the hydrology. If that is true, then the clusters that are emerging should be connected to the actual landscape, right? I mean, like if the data is actually true, it should be connected. So there's two problems that can emerge. If the data, the spatial data that I'm using is a very poor low quality or very poor quality, then yeah, the clusters that I'm having are pretty much just random, right? But in general, what I will say is that the topography data that we have is pretty good. I mean, like, the only thing that I would say is like in situ soil moisture probes. Yes, in theory, those are like the scales of that's like meter scale. And so we only have like 30-meter, 100-meter scale information. So there is sub 30-meter information that indeed could be playing out that could explain still the large differences that exist between my clustered simulation and that of the in situ. But I mean, from what we've been seeing, like there still are deficiencies. I mean, we did over the entire US where this whole simulation, and then we started asking the question of what happens if you upscale. So if you compare it 100 meters versus 1 kilometer versus 10 kilometers, then see the situ probes, is there a difference in performance of the model? Over like 1,000 in situ probes. And the answer was yes, there was a slight improvement by doing this, right? Like you could see a slight improvement in terms of like how well your model's able to reproduce if you compared it 100 meters, but it wasn't significant. I mean, it wasn't that large to be like, yes, this makes a huge difference in being able to reproduce that.
Well, you said yourself, right, that there's still huge uncertainties in the soil properties, right? So we don't even know if we're, and kind of like to Allegra's point, like, you know, you can compare the probe at 100 meter, you can compare the same spot in the model, but we don't even know if the model is set up to do the best simulation it can.
Yeah, but this goes back to then the idea that we talk about how we can't compare our models to the in situ probes, right? Because of the scale issue. So what I'm trying to say here is this brings to light a bigger problem, which is that the data that we have is not that good, and that there is a process representation that might not be there that's also representing that in situ process. So the thing is, it allows to connect our models much more to the in situ problem, and it allows us to be a little more critical and think more about the data problem instead of just saying scale disconnects, I can't work with that data.
Right. The issue isn't the scale, it's that we're just not representing the real world.
One discussion, I guess, urban areas, does that slot nicely into all this?
It would.
Urban.
I mean, you can cluster according to urban characteristics. I mean, like you can. I have not spent a lot of time on that. You can also think about water management. You can think about irrigation in this context. So, like, what type of irrigation is happening over the landscapes? You can do that as well, and you can connect it so you can have the irrigation draw from the closest river, from the riparian zone. So you connect it to the tile that it's actually drawing water from. So in urban areas, you can split it up. So I mean, we cluster. I don't show it here, but we cluster on urban areas, and you're able to see the high sensible heat flux from those urban areas.
We do have one hand raised online, so if Dorothy, you want to unmute yourself?
Thanks. Yeah, I might have missed this because I missed the beginning of your talk, but what do you have wetland vegetation with moss and wetland species in some of the tiles, in the low elevation tiles in particular, that would change things?
So, okay, so there's two implementations of this that I showed. One was like the original toy bot, like the sandbox model HydroBlocks is what we would do. That does not have wetlands. The GFDL one will have wetlands. I can't speak too much about it because I don't really work in that area, but one of the reasons for the development of this hill slope model was for wetlands. That's why they did it. So they will have their different vegetation within the wetland itself.
Well, thank you. I guess we're at time. So
Yep.
Yeah.
Thank you.
We're having a more extensive discussion at 3 to 4, actually maybe 3 to 3:30 p.m. today, because we have to speaker has to get to as flight. So thanks, and hopefully see more.
Starts at 3?
Well,
We can
because
start earlier. I mean,
CCSR is having its